Yeah, good evening again. This is, you can say it is last lecture of mole and stoichiometry. So we conclude this chapter. We'll do some basic theory part remaining for the chapter, and we'll do many questions based on this. So till now, in mole and stoichiometry in the last lecture, we have just finished the calculation of n factor related to different type of substance, including valencies, valency for element. It is basicity for acid. It is going to be, acidity for base. It is total positive charge and negative charge for its ions per molecule of the salt. And more important thing is it is number of electron transfer for any reducing and oxidizing agent. So to revise the same thing again, let's say, if you see equivalent mass, definition of equivalent mass or formula of equivalent mass. So equivalent mass should be equal to, you can say it is molar mass divided by n factor. And we know this n factor can be valency for element, this can be basicity for acid, it is acidity for base, it is total positive or negative charge on its ions per molecule, and it is total number of electron get transfer in the case of redox reaction. So total number of electron transfer per molecule or atom of reducing and oxidizing agent in redox reaction. For example, if you see one of the redox reaction as, if it is, let's say, Cu2s plus, you can say it is KMnO4, potassium permanganate, in acidic medium. Suppose its product is found to be cupric ion, its product is found to be sulfate, it is found to be Mn2 plus and K plus and let's say H2O. In this case, oxidation number of sulfur is -2, which increased up to +6. I hope you can easily figure out these change in oxidation number. Oxidation number of copper initially was, let's say you can say +1, and it get increased up to +2. Oxidation number of manganese was, you can say it is +7, which can increase up to +2. Which can decrease, let's say from +7 to +2. So here you can say KMnO4, in which oxidation number decreases, serve as a oxidizing agent, it get reduced itself. And Cu2s is going to be, a reducing agent. So we have reducing agent, we have oxidizing agent here. As per reducing agent is concerned, its equivalent mass should be equal to its molar mass. Let's say you can say its molar mass is M1 divided by number of electron get transferred per molecule. So if you see copper get oxidized from +1 to +2, so number of electron get transferred for copper only should be equal to, let's say, twice of 2 minus 1 plus, 8 more electron get transferred for sulfur, which may be written as change in oxidation number as 6 minus of -2. And in this case, it is M1 divided by 10. Its equivalent mass should be nothing but, let's say, M1 divided by 10. In the case of KMnO4, the equivalent mass should be equal to, its molecular mass divided by number of electron get transferred. It is from +7 oxidation number decreases to -2. So you can say it is M2 divided by, 5. So they are respective, you can say equivalent mass in terms of their respective molecular mass. So it is number of electron get transferred per molecule of reducing agent or number of electron get transferred per molecule of oxidizing agent. In today's lecture, we will see a few common oxidizing agents first, including KMnO4, K2Cr2O7, H2O2, and then we'll see the significance of law of equivalence. We'll apply law of equivalence without balancing the reaction. But it is just a revision of whatever we have done in the last lecture related to calculation of equivalent mass. I hope you understand the concept of equivalent mass. It is molar mass divided by n factor, and n factor can depend on type of the species. For example, I'm repeating again, for element, it is molar mass divided by valency. For acid, it was, molar mass divided by basicity of the acid. Basicity means number of H plus get transferred per molecule, number of H plus get furnished per molecule by acid in its aqueous solution. Same in the case of base, equivalent mass equal to, molecular mass divided by number of OH minus ion get furnished per molecule. And there's the last thing related to redox reaction. Equivalent mass is molar mass divided by number of electron get transferred per molecule, and same in the case of KMnO4. Equivalent mass is molecular mass divided by number of electron get transferred per molecule. So next thing, apart from, let's say, equivalent mass, common oxidizing agent. Common oxidizing agent, one of the most common oxidizing agent is potassium dichromate only. Yeah, first you can say potassium permanganate. Potassium permanganate. So potassium permanganate is nothing but, you can say, it is KMnO4. KMnO4, potassium permanganate. So it is useful. It is useful oxidizing agent. It is useful oxidizing agent in all mediums. All mediums means it serves as an oxidizing agent in acidic medium, basic medium, as well as in neutral medium. For example, let's say its A part is, in acidic medium. In acidic medium, it is permanganate ion. In acidic medium can gain few electron. It can be converted into Mn2 plus and let's say H2O. Here number of electron get transferred. It is +7 oxidation number of manganese, decreases to +2 oxidation number of manganese here. And 5 electron get transferred here. So +7 oxidation number, it will gain 5 electron, decreases to +2 oxidation number here. If you have to balance this reaction completely, 4 oxygen, so we should have 4 H2O here and should have 8 H plus here. So it is completely balanced reaction. in which 5 electrons get transferred per molecule of KMnO4. So you can say as oxidizing agent, as you know, oxidizing agent equivalent mass of KMnO4, obviously in acidic medium, should be equal to its molecular mass divided by number of electron get transferred per molecule is 5 here. As from balance reaction, you come to know 5 electron get transferred per molecule of KMnO4. Same, let's say in B part. In basic medium, corresponding reaction may be written as, let's say, permanganate ion gain 1 electron and it can convert into magnate ion. Again, if you see the color of permanganate ion is nothing but purple, and the color of MnO4 2- is found to be green. Here only 1 electron get transferred. So in this case, the equivalent mass of KMnO4, in terms of their molecular mass is M divided by 1. So potassium permanganate, it is useful oxidizing agent in all mediums. For example, in acidic medium, it is permanganate ion H plus 5 electron will give Mn2 plus H2. As a oxidizing agent, equivalent mass of KMnO4 is M divided by 5. And basic medium, equivalent mass of KMnO4 is M divided by 1, let's say. I hope you have noted down this. Same as C part of KMnO4 only. In neutral medium. In neutral medium, it is permanganate ion plus, it is H2O. It will gain 3 electron, will convert into MnO2, and let's say 4 OH minus. So it is 2 H2O in balance reaction, in which again manganese having +7 oxidation number here, and it has +4 oxidation number. So again, its color is found to be purple, and it is found to be, black precipitate. As per MnO2 is concerned, it is found to be, let's say, black precipitate here. In this case, equivalent mass of KMnO4. Equivalent mass of, KMnO4 is its molecular mass divided by 3. Its molecular mass divided by 3. Now, depending on, KMnO4 and factor in different mediums, they required many such type of questions. For example, one of the situation may be related to the question 1 is related to N factor calculation or equivalent mass calculation. So, equivalent as in acidic medium, as oxidizing agent. in acidic medium as oxidizing agent, equivalent mass of KMnO4. You can say equivalent mass of barium permanganate, and you can say it is equivalent mass of aluminum permanganate. As per KMnO4 is concerned, as we have only one electron get transferred per ion of, let's say, permanganate ion, 5 electron get transferred for 1 permanganate ion, so 10 electrons should transferred for 2 permanganate ion, and 15 electrons should transferred for 3 permanganate ion in acidic medium. So in this case, its equivalent mass can be M1 divided by 5. It should be M2 divided by 10, and it should be M3 divided by 15. They are the respective equivalent mass of different type of species here in acidic medium. It is M1 by 5. In the case of barium permanganate, it is M2 by 10, and in the case of aluminum permanganate, it is M3 divided by 15. Another possibility of such type of question may be. So next one is question 2. Based on this, find out minimum moles of KMnO4 required to oxidize. Find out minimum moles of KMnO4 required to oxidize 5 moles of I2 into IO3 minus in neutral medium. Okay, so in repeating again, question is find out minimum moles of KMnO4 required to oxidize 5 moles of I2 into IO3 minus in neutral medium. So as per answer of the question is concerned, obviously one of the reagent is KMnO4 as the oxidizing agent, and another is going to be, let's say, I2 here. And the oxidation of I2 has to be in, let's say, IO3 minus. We already know N factor of KMnO4 in neutral medium as an oxidizing agent. If you see your class notes, if you refer your class notes, it is going to be N factor as 3, since in neutral medium, manganese plus 7 oxidation number get decreased up to, let's say, plus 4 oxidation number. And similarly, in the case of iodine, its oxidation number is 0 and its oxidation number is going to be, it is plus 5. So N factor of I2, N factor of I2 is going to be, let's say, 10 here. Since per iodine atom, it will lose, 5 electron, and, for I2 molecule total, it will lose 10 electrons. So its N factor is 10, its N factor is 3. Here you can imagine, let's say, X moles of KMnO4 is required to oxidize 5 moles of I2, and according to law of equivalence. According to law of equivalence, total equivalence of oxidizing agent should be equal to total equivalence of reducing agent. So 3 times of X should be equal to 5 times of 10, and from here X should be equal to 50 by 3. from here, X equal to 50 by 3 moles. So it is 50 by 3 moles of, KMnO4s will be required to oxidize 5 moles of I2 into, let's say, IO3 minus. So I hope you can remember the N factor of KMnO4 in different types of medium and different type of pH. Repeating again, in acidic medium, its N factor is going to be 5. In neutral medium, its N factor will be, 3. And in basic medium, its N factor is going to be 1. Now, apart from potassium permanganate, another common oxidizing agent is potassium dichromate. So let's say B part is potassium dichromate. It is K2Cr2O7. So it is another useful and strong oxidizing agent. I hope you heard about this potassium dichromate and potassium permanganate. Usually it is present everywhere in chemistry lab of every school. So potassium dichromate, you can say it is, useful oxidizing agent, but only in acidic medium. So it is useful oxidizing agent, but only in acidic medium. And if you see corresponding reaction here, it is, dichromate ion. Why we writing only dichromate ion instead of K2Cr2O7? There is no change in oxidation number correspond to potassium. By rule, potassium, which is alkali metal, its oxidation number is going to be +1 in combined state in any of the compound. So there will be no change in oxidation number of potassium. So you have to just write dichromate ion only. So in balance reaction, you can say it is 14H plus. That's the 6 electrons. It will give 2 chromium 3 plus, and let's say it will give 7H2. In this case, oxidation number of chromium is found to be +6 here. Oxidation number of chromium is going to be +3 here. So there is a reduction of, potassium dichromate, and it gave, let's say, chromium 3 plus in given reaction. So it is useful oxidizing agent, but it is useful only in acidic medium. As per color of dichromate ion is concerned, its color is, let's say, orange, and color of Cr3 plus is going to be green. So equivalent mass of, K2Cr2O7 in acidic medium. Equivalent mass of K2Cr2O7 in acidic medium should be equal to, its molecular mass divided by 6. Number of electrons get transferred per molecule of potassium dichromate. You should remember the N factor of KMnO4, K2Cr2O7, and we'll see one more common oxidizing and reducing agent, that is hydrogen peroxide. If we do similar type of questions for potassium dichromate also, so one of the question based on, oxidation by potassium dichromate is, find out minimum moles of K2Cr2O7 required in acidic medium. Find out minimum moles of K2Cr2O7 required in acidic medium to to oxidize. Find out minimum moles of K2Cr2O7 required in acidic medium to oxidize. Let's say 6 moles required to oxidize 6 moles of AS2S3 into ASO4 3 minus and sulfate ion SO4 2 minus. So again, as per let's say answer is concerned, one of the compound is going to be potassium dichromate. Another compound is going to be, let's say, AS2S3. AS2S3 is going to be oxidized into ASO4 3 minus, and it is going to be oxidized into sulfate ion. As per N factor of potassium dichromate is concerned, it is going to be 6 here. We know it in acidic medium. Its oxidation number decreases from +6 to +3 per chromium. 3 electron will transfer, and for 2 chromium atoms, 6 electron will be transferred. Same in the case of AS2S3, its oxidation number is going to be +3, sulfur oxidation number is going to be -2. Arsenic oxidation number is +5 and sulfur oxidation number is going to be +6. So change in oxidation number of arsenic, it is going to be +3 to +5, and sulfur is going to be it is -2 to +6. So from +3 to +5, 2 and 2, let's say 4. So as per N factor is concerned, arsenic, for arsenic only, 4 electron get transferred, and for 3 sulfur atom, another 24. So 24 plus 4, total 28 electron get transferred. Again, you can just try to see how we calculate the N factor of AS2S3. In the case of arsenic, its oxidation number increases from +3 to +5 for 2 arsenic atoms. So total in general, you can say 4 electron it will lose for arsenic only. In the case of sulfur, its oxidation number increases from -2 to +6. So 8 electron get transferred per sulfur atom, and for 3 sulfur, total 24 electrons get transferred. So 24 plus 4, 28 electrons get transferred for AS2S3. Now, in the case of K2Cr2O7, its number of moles is suppose, let's say, X moles, and its number of moles, let's say 6 moles as given in the question. According to law of equivalence, its N factor multiplied by number of moles should be its N factor multiplied by number of moles, and X comes out to be 28 moles. So my point is, there is no need to balance these redox reaction. You can directly apply law of equivalence concept. According to law of equivalence, whatever equivalence of reducing agent get consumed, it should be same as the number of equivalence of oxidizing agent present. Now, apart from potassium dichromate and potassium permanganate, third C part, let's say common oxidizing agent is, it is hydrogen peroxide. Another common oxidizing agent is, it is hydrogen peroxide. As per hydrogen peroxide is concerned, it is useful reducing as well as oxidizing agent. It is useful reducing as well as oxidizing agent in both acidic as well as basic medium. So hydrogen peroxide H2O2 is useful reducing agent as well as oxidizing agent in both acidic as well as basic medium, and fortunately with the same N factor. So with the N factor of N factor of fortunately 2. So either it is reducing agent, either it is oxidizing agent. Its N factor of H2O2 is fixed as 2 only. Now if you see corresponding reaction here, let's say H2O2 can oxidize to give O2, and H2O2 can reduce to give H2O. So in given reaction, H2O2 serve as reducing agent, it will oxidize itself, and it is as oxidizing agent, it will reduce itself. So it is -1 oxidation number to 0, and it is -1 oxidation number to -2. So as reducing agent, we have oxidation of H2O2. As oxidizing agent, we have reduction of H2O2. In both case, 2 electron get transferred. Either it behave as a reducing agent, either it behave as a oxidizing agent. Here simply you can say it will lose 2 electron, and here you can say it will gain 2 electron. So in any redox reaction, equivalent mass the equivalent mass of H2O2 should be equal to its molecular mass divided by 2 only. So molecular mass, we know it is 34 divided by 2 comes out to be 17. it is going to be equivalent mass of H2O2 in any of the redox reaction. So as per H2O2 is concerned, it is useful reducing as well as oxidizing agent. But in acidic as well as basic medium, its N factor is going to be, let's say, 2. And I hope you have noted down this H2O2. Here we have one more term related to H2O2 only. This term is known as volume strength of H2O2. So volume strength of H2O2. As per concentration term volume strength, it is defined only for the solution of H2O2. So volume strength of H2O2, similar to any other peroxide, H2O2 is also unstable. It can decompose with time. So if, on complete decomposition, if on complete decomposition, so if on complete decomposition of H2O2, complete decomposition of 1 milliliter of H2O2 solution, if on complete decomposition of 1 milliliter of H2O2 solution, it gives X milliliter of O2 at NTP. If on complete decomposition of 1 milliliter of H2O2 solution, it gives X milliliter of O2 at NTP, then volume strength of H2O2 solution is, it is X volumes. So if on complete decomposition of 1 milliliter of H2O2 solution, it gave X milliliter of O2 at NTP, then the volume strength of H2O2 solution is X volumes. The volume strength of H2O2 solution is X volumes. For example, let's say it is H2O2. On its decomposition, it can give H2O and let's say half O2. It is decomposition of hydrogen peroxide H2O2 solution. It is typically disproportionate reaction in which oxygen having -1 oxidation number decreases to -2 and increases to 0. So in this given redox reaction, no separately reducing and oxidizing agent. Same compound H2O2 get reduced as well as oxidized here. Now further, in the case of H2O2 solution, if molarity of given solution given solution is m moles per liter, if molarity of given solution, it is m moles per liter, then in 1 milliliter of H2O2, in 1 milliliter of H2O2, we should have m divided by 1000 moles. Obviously, m moles per liter means 1000 milliliter consists m moles, so 1 milliliter consists m divided by 1000 moles. Now, if you see the stoichiometry, 1 mole of H2O2 will give half moles of O2. So m divided by 1000 moles should give, half of m divided by 1000 moles of O2. So volume of O2 at NTP should be equal to half of m divided by 1000 multiplied by 22.4 multiplied by 1000 milliliter at NTP. Now, if you remember, it is 1 mole of gas occupied 22.4 liter at NTP. And if you do a calculation further, it comes out to be 11.2 multiplied by m milliliter at NTP. Now, if you see the definition again, volume strength of H2O2, if on complete decomposition of 1 milliliter of H2O2 solution, it gives X milliliter of O2 at NTP, then the volume strength of H2O2 solution is X volume. So here we know on complete decomposition of 1 milliliter of H2O2, it gives 11.2 multiplied by molarity, milliliter at NTP. So here confirmly you can say volume strength of H2O2 should be equal to, you can always remember, 11.2 multiplied by molarity. 11.2 multiplied by, let's say, molarity. And you need to remember this formula. Volume strength of H2O2 is 11.2 multiplied by molarity. So if on complete decomposition of 1 milliliter of H2O2 solution, it gives X milliliter of O2 at NTP, then the volume strength of H2O2 solution is, let's say, X volumes, such that on complete decomposition of 1 milliliter of H2O2 solution, it gives M milliliter, it gives M multiplied by 11.2 milliliter of O2 at NTP. And from here you can say volume strength of H2O2 is 11.2 multiplied by molarity of H2O2. More important thing is, next definition related to this is normality. Its symbol is capital N. So as per normality is concerned, it is something very similar to molarity as we have defined in, concentration terms. Molality, percentage by weight, percentage by volume. So normality. Now normality is equivalence of solute dissolve in. It is equivalence of solute dissolve in 1 liter of solution. Normality is equivalence of solute dissolve in 1 liter of solution. So from here, if you see normality, which is capital N, should be equal to equivalence of solute divided by volume of solution in milliliter multiplied by 1000. Normality, equivalence of solute dissolved in 1 liter of solution. So here normality N comes out to be equivalence of solute divided by volume of solution in milliliter multiplied by 1000. So molarity was number of moles per liter. Normality is equivalence of solute per liter of solution. So further, as per normality is concerned, which is equivalence of solute per liter of solution. So normality is equivalence of solute per liter. As per normality is concerned, it is equivalence of solute per liter should be equal to molarity multiplied by n factor, as molarity is moles of solute per liter of solution. Now, this we already know. Number of equivalence is nothing but n factor multiplied by number of moles. And from here, you can simply say equivalence of solute should be equal to normality, which is capital N, represented by capital N, multiplied by volume of solution in liter. Obviously normality equivalence per liter, and multiplied by volume of solution in liter. Okay, so as per equivalence of solute is concerned, equivalent solute per liter is normality, and you can easily find out equivalence of solute by multiplying normality and the volume of the solution. Back to this concentration, volume, and all these things. So it is known as titration, or you can say it is volumetric analysis. Titration or volumetric analysis. Usually the purpose of this titration or volumetric analysis is to find out unknown concentration. To find out unknown concentration or molarity. For example, if you see complete setup can be something look like this. Suppose in this beaker we have some, some substance. You can imagine this beaker may have certain substance as this. So suppose this beaker have some reagent here, and this reagent may be, let's say, any, reducing agent, oxidizing agent, or anything. But suppose its molarity, M1 is not known, it is unknown, and the purpose of this titration or this, volumetric analysis is to find out the molarity only. With the help of measuring flask in lab, you can easily find out its volume. So let's say this volume is found to be V1 and its molarity M1 is unknown. So you can choose any of the, another reactant which can react with this substance, and it may be taken in the burette. This reagent may be taken in burette. I hope you are aware about this type of, glass tube which is known as burette. Usually it is kept on a stand in lab. And from burette, suppose here some specific substance is filled completely in this burette here, which can react with given substance. So here it can react with given substance, and in this case, suppose the molarity of given substance is, it is M2, and which is known. It is M2 as a molarity which is known to us, and you can simply imagine, let's say this much volume get consumed for its reaction with reagent. So here you can imagine this may be, suppose, reactant 1, and here in burette we can have, let's say, reactant 2. Now at equivalence point, at equivalence point, the number of equivalence of given reactants should be equal to number of equivalence of another reactant. So according to law of equivalence, total number of equivalence of both reactants should be equal. So here you can say equivalence of reactant 2 added from burette should be equal to equivalence of reactant 1, present in vessel. Now during the reaction, suppose you can simply imagine, let's say if its N factor is N1 and its N factor is N2. So number of moles may be N1, or you can say its N factor is N1. Number of moles may be molarity multiplied by volume should be equal to, N factor times of number of moles, or this equation may be written as N1V1 should be equal to N2V2. Normality is nothing but N factor multiplied by molarity. N1V1 means equivalence per liter multiplied by volume in liter will be number of equivalence. Same N2 multiplied by V2 is equivalence of solute per liter multiplied by, let's say, volume in liter. So to find out, let's say, molarity of unknown concentration or unknown substance, you can use this titration method. So in typical parameter N1 V1 equal to N2 V2, 3 terms can be given to you in the question and you have to find out the fourth one. We'll do a couple of questions based on this normality, molarity terms. I hope you note down this titration. So we'll do a couple of questions. Let's say question number 1 based on this is, find out minimum volume of 0.2 molar acidified KMnO4 solution required to oxidize. Find out minimum moles, minimum volume of 0.2 moles per liter acidified KMnO4 solution required to oxidize 30 milliliter of 0.5 molar ferrous sulfate, FeSO4. So this is a typical question of titration, redox titration, in which we have one as a reducing agent, another as an oxidizing agent. So, it is KMnO4 potassium permanganate and it is FeSO4 as a reducing agent. Oxidation number of manganese is +7 here and oxidation number of iron is, let's say, +2 here. As per KMnO4 is concerned, it is oxidizing agent and FeSO4 is going to be reducing agent here. At equivalence point, first its N factor is found to be 5 and its N factor. Ferrous sulfate will oxidize to give ferric sulfate. So from oxidation number of +2 in iron, it will increase it up to +3. So its N factor is going to be 1. Number of equivalence of reducing agent should be equal to number of equivalence of oxidizing agent, such that you can say its N factor as a 5 multiplied by its molarity was 0.2 and you have to find out its volume of KMnO4. So N1 M1 V1 should be equal to N2, its molarity is given as 0.5 and typically its volume is given as 30 milliliter. So as per this volume, as per volume of KMnO4, acidified KMnO4 is concerned, it comes out to be 30 divided by 2. It is 30 divided by 2 and it comes out to be 15 milliliter. So 15 milliliter of KMnO4 will be required to oxidize 30 milliliter of 0.5 molar FeSO4 completely. I will show you two more questions related to this type of calculation. Just note down this. Now, second question based on this is, if 30 milliliter of 0.2 molar H2SO4 is mixed with 20 milliliter of 0.15 molar NaOH solution, then find out volume of 0.12 molar calcium hydroxide required to neutralize above solution. Find out volume of 0.12 molar calcium hydroxide required to neutralize above solution, in which already we have H2SO4 and NaOH. So one of the compound is, H2SO4. Another compound may be, let's say, NaOH, or this compound may be, let's say, calcium hydroxide. The N factor of H2SO4 as an acid is 2. N factor of NaOH is 1. And N factor of calcium hydroxide is, let's say, 2 here. Now, as per H2SO4 is concerned, it is 30 milliliter and 0.2 molar. As per NaOH is concerned, it is 20 milliliter of 0.15 molar. And it is X milliliter of 0.12 molar. So here we have one acid and two different bases. According to law of equivalence, total equivalence of acid should be equal to total equivalence of base, such that N factor of acid as 2 multiplied by its molarity and, let's say, volume. So there will be number of equivalents, so milli equivalence of H2SO4 should be equal to its N factor as a 1 it is 20 multiplied by 0.15 should be equal to, or it is plus total equivalence of acid should be equal to total equivalence of base should be twice of x multiplied by 0.12. And from here, x comes out to be. Yeah, just calculate the value of x from here. So it is basically 12, and it is minus of 12 minus 3 divided by 0.24. So it is 8 divided by 0.24 comes out to be, it is how much? It comes out to be 100 by 3 technically, or you can say it is 33.33 milliliter of calcium hydroxide is required. So it is the example in which we have only one acid and two different bases are present. And you can find out their n factor easily. Acid ka n factor means, the meaning of n factor of acid is number of replaceable H plus ion. In the case of H2SO4, its n factor is going to be 2. And in the case of bases, for example, NaOH and calcium hydroxide, their respectively n factor is 1 and 2. NaOH base n factor is 1, calcium hydroxide as a base, its n factor is going to be 2, let's say. So another question. So one more question related to this is, if 30 milliliter of H2O2 solution can oxidize 50 milliliter of an aqueous solution containing 0.2 molar 0.2 molar ferric oxalate into, obviously the highest oxidation number of iron is usually +3, and CO2. Then find out volume strength of H2O2 solution. If 30 milliliter of H2O2 solution can oxidize 50 milliliter of an aqueous solution containing 0.2 molar ferric oxalate into Fe3 plus ion and CO2, find out the volume strength of H2O2 solution. So here we have H2O2 and here we have, ferric oxalate. The n factor of H2O2 is 2 and the n factor of ferric oxalate is going to be, 6. Here every carbon from +3 oxidation number increased up to CO2, in which oxidation number of carbon is going to be, let's say, +4. Now suppose if its volume strength is X volumes, then we know its molarity should be X divided by 11.2 molar. Here it is given as 0.2 molar and its volume is given as 50 milliliter. Its volume is given as 30 milliliter. So according to law of equivalence, their number of equivalents should be equal. So n factor, which is going to be 2 multiplied by its molarity, is X divided by 11.2 multiplied by volume 30, should be equal to, its n factor is going to be, let's say 6. It is 0.2 multiplied by 50, and from here value of X should be equal to. So it is 50 into 6 multiplied by 0.2, it is 60, and from here X comes out to be 11.2 volumes. So as per volume strength of H2O2 solution is concerned, in this case is found to be 11.2 moles per liter, sorry 11.2 volumes as a volume strength is concerned. I hope you understand the term, what is the meaning of titration or volume strength, or volumetric analysis here. So that's all for this chapter, moles and stoichiometry. So in this chapter, again I'm repeating, we have revised the basic calculations of moles and stoichiometry, balancing of redox reaction, concept of equivalent mass, law of equivalence, titration, and volumetric analysis. So from the next lecture onward, we'll start new chapter known as chemical bonding. Up to that, keep solving, keep practice related to mole and mole stoichiometry. So I'm going to bind up now. Thank you.